Welcome, everyone. For today's prep, we're going to look at integration. We're going to start with integration. And today we're going to introduce antiderivatives and indefinite integrals. All right, so the underlying question here is, let's suppose everything we've done in the class so far we've been working with functions, and we've learned a whole bunch of rules that allow us to calculate the derivative of a function. So we call that process differentiation. So we've learned a whole bunch of things where we take a function f, and through different rules we get a new function which we call f prime. So the question is, if we know the derivative, so if we only know f prime, is it possible to recover this original function? So is it possible to go back? And the answer is yes, but not quite, not fully. So the technique we're going to call, or this process we're going to call integration. So if we have the derivative, it is, for the most part, possible to go back to the original function. The only issue that we're going to see is this differentiation process does destroy a little information about the original function. So we're not going to be able to go all the way back completely just by knowing the derivative. We'll see that later on. But for right now, we want to think of integration as basically gets the job done. So it basically takes our derivative and it does send us back to the original function. All right, so let's introduce a little bit of terminology. So we say that a function capital F is an antiderivative of function little f if the derivative of capital F is equal to little f. So there's a lot of different functions going on here. So let's do a little diagram to keep track of these. So we're going to have a function capital F, and we're going to call this the antiderivative. And then we're going to have another function, little f, and we're going to consider this the derivative. So you can almost think of these two functions, they kind of form like a pair. So if we go one way, and if we differentiate, so if we take our antiderivative and we differentiate, we should get f of x. We should get its derivative. And if we take little f, and we're going to see if we do the integration, we should get our antiderivative. So I'm going to abbreviate that I for short. So we have these pairs of functions, or classes of functions. So we have our antiderivative and then our derivative. So how are we going to check this? Let's look at an example to kind of get an idea of what's going on with this diagram. So let's look at the function little f of x equal to x squared. And we're going to show that the function capital F1, which is 1/3 x cubed, is an antiderivative of this. And we're going to show 1/3 x cubed plus 1, a different function, which we'll call f2, is also an antiderivative. So how do we show that something is an antiderivative? Well, if we want to show that this is the antiderivative of little f, we're going to differentiate. So let's take our function 1/3 x cubed, and let's do the derivative of that. So that'll give us f1 prime. And let's just do regular power rule here. So the 1/3 is a constant multiple. It just stays out in front. We do power rule on the x cubed. We get 3x squared. And then if we simplify, the 3 and the 1/3 cancel, so we're left with x squared. And that is our function little f of x. So, yep, it's an antiderivative. So if we start with what we think is the antiderivative and we differentiate it, we get the x squared function here. Now, let's try the second one. So let's start with this other function. So this one's called f2 because it is technically different. So we're going to start with 1/3 x cubed plus 1, and we're going to differentiate this. So let's go do our derivative. And this will, when we differentiate, this will give us f2 prime. And when we differentiate, the 1/3 is still a constant multiple. Differentiate the x cubed, we get 3x squared. And then the derivative of that plus 1 is 0. So we have plus 0. And if we simplify, it simplifies to just x squared again. All right, so that is showing that this is also an antiderivative. So this kind of illustrates the main issue, one of the issues with integration. And that is, if we have a function x like x squared, it actually has an infinite number of possible antiderivatives. So we can see that there's like the main part here, which does most of the heavy lifting in terms of being the antiderivative, but then we could just add on a different constant, and we also have the same we also have a new antiderivative. And this is just kind of what happens. So we have a theorem here that says if we have two antiderivatives, capital F1 and capital F2, so if these are two antiderivatives of a continuous function little f, well then they're basically equal to each other, except they might differ by a constant. So we're going to throw on this this plus c here. So the two different antiderivatives, basically they're going to be the same. The main variable parts are going to be the same. They might just be different by just a constant here. And we'll look at the significance of this constant c a little bit more in class, but you can kind of see here we have the graph of that antiderivative 1/3 x cubed plus 1. Here we have the graph of the antiderivative 1/3 x cubed. And you can see that these graphs are really kind of parallel to each other, almost like parallel lines. All right, so we'll talk more about this, these two graphs in class. But right now we just want to think, if we have two antiderivatives, they differ by a constant, or they might differ by a constant. And so because of that, we're going to use this notation. If we have a function little f of x, and we want to find its derivative, we're going to use this integral symbol. So this symbol here, it's really a stretched out s, and this is what we're going to call our integral symbol. And then the function we're integrating is dx. Or no, the function we're integrating is f of x. And sometimes we'll call that the integrand. It's the thing we're integrating. It's the thing we're trying to find the antiderivative of. And then on the other end of things, we have this dx. And this is called the differential. So basically, the way we read this is the integral sign, really, it's a stretched out s, and we'll see why it's a stretched out s. It actually stands for sum. But right now, it's just this integral symbol. And the way we read this is it means find the antiderivative of the function f of x with respect to x. And once we find one antiderivative, we know that there's a whole bunch more. So just to indicate that, we're going to just add on plus c. So we're just going to leave this as a general plus c because we know all of the antiderivatives, the main variable part is going to be exactly the same. It's really, they're just going to differ by a constant. So rather than trying to distinguish between all these slightly different antiderivatives, we're going to have our main variable part, and then we're just going to put plus c at the end. So that's just something to remember. We'll star that. All right, so it's a little thing, but we'll see that this actually does have some significance. All right, so this notation, this integral symbol, and I guess we could compare this. So when we have this integral symbol in dx, the way we read this is find the antiderivative of the function f of x with respect to x. So this is similar to our derivative notation, the Leibniz form. So when we looked at derivatives, this is one of the versions of our differentiation notation. And the d means find the derivative of the function inside the brackets. And then the dx means with respect to x. So you want to think of the integral sign and the dx for right now as just kind of notation telling us something similar to what the d dx notation says. All right, so let's see what this integration does. So let's say we started with a function little f and we integrated it. Well, then we'll get something called the antiderivative, and we have the integral of f of x dx. Now let's suppose we take this result and we then differentiate it. So when we differentiate that, what we get back, what we get out, is just the original function. So if we take a function little f and we integrate, we get something called the antiderivative, and then if we differentiate that, we get our little function. We get our function little f back. So it is helpful to think of integration and differentiation. They're kind of the two processes that undo each other. Now, if we start with capital F, and if we start by differentiating that, well, then we're going to have the derivative of f of x. And then if we take that derivative and we try to integrate, what we're going to get out of this is capital F, but not quite. So plus c. So we almost get back the original function, but we might be off by a constant. So this derivative here does destroy a little bit of information about the original function that integration doesn't fully recover. But still, it's helpful to think of doing a derivative and an integral. They really just kind of cancel each other off. Doing an integral and then a derivative, they just kind of cancel each other off. All right, so let's look at just a couple basic antiderivative rules to get a little taste of how this is going to work. So let's look at a constant. So if we're trying to integrate a constant, we're trying to find the antiderivative of the constant function k. K is just some number here. And again, remember, we're finding the antiderivative of constant function k with respect to x. So what we do is we keep the constant, and then we just multiply by our variable. So we end up with k times x. And for any of these general antiderivatives, we're going to just put plus c on at the end. So it should be kind of come automatic almost. So that's for a constant function. Now the other kind of the most basic function that we're going to consider is a power function. And so it's going to be helpful to know what's the antiderivative of a power function. So if we're trying to find the antiderivative of x raised to the power n with respect to x, well, this is going to, again, we're kind of undoing the derivative. So it's going to look kind of similar to our derivative power rule, but we're undoing it. So what happens? Well, we're going to keep our variable x the same. We're going to add 1 to the exponent. And then we're going to take our new exponent and we're going to flip it and put it in front. So you want to think of this number in front here. This is just the reciprocal of the new exponent. Now, the one thing with this power rule is it doesn't always work. So there's one exception, and that is if this exponent n is -1. So it's worth just remarking here. If n does not equal -1, or if n, let's say n is equal to 1, -1, then we need a different rule. And we'll see what this is a little bit later on. Hint, it's going to involve natural log. All right, so let's try out a couple examples of some power rule and constant rule. So let's look at the first example here. We want to find the most general antiderivative for each of these functions. So let's start with the first one. This is just the constant function 5. So we want to find the general antiderivative. So we're going to integrate the function 5 with respect to x. And we know with respect to x because that's the variable for our function here. And when we do this, we keep our constant. And we know the variable is going to be x, so we multiply by x. And then we add c on. All right, so integrating a constant. Let's try the next one, integrating x cubed. So we want to find the general antiderivative for this. So we're going to integrate x cubed with respect to x. So how is this going to work? So let's try out our power rule on this. So when we do our power rule, you want to leave a little space in between the equal sign, and we're going to put our variable x down. So leave a little space here. And then we're going to take our old exponent and we're going to add 1. So we're going to get 4. And then we take this new exponent and we flip it. Put the reciprocal in front. So we get a 1/4 in front. And then at the very end, we want to remember our plus c. Okay. And there it is. We've got our antiderivative. Now let's try square root x. And as usual, when we have root functions, kind of the same strategy as with derivatives, we want to rewrite this. We want to rewrite the nth root of something as raised to the power 1/n. So for square root, it's going to be raised to the power 1/2. So really what we're trying to do here is we're trying to integrate the function x raised to the 1/2. So square roots are fine, but for power rule, we want it as a power function. All right, so let's try it out. So our variable is x, and we're going to add 1 to the exponent. So we go from 3, well, I spoiled it, 1/2 to 3/2. We take this new exponent, and then we flip it, and we put the reciprocal in front. So the new exponent is 3/2. So when we put the reciprocal in front, it's going to be 2/3. And then we just remember our plus c. All right. So we'll practice more of these in class, but just wanted to kind of get an introduction to integration. And where we're going with this is we're going to learn, well, a whole bunch of different integration rules, kind of like what we did with derivatives. So we'll see you then. Bye-bye.